Hi everyone, this is Dr. Sirisha working as Associate Professor in Institute of Aeronautical Engineering College. In our previous session, we have seen sorting techniques. We got an introduction of sorting techniques and we have seen the first basic sorting technique, which is a bubble sort, right? In which the logic was to compare between two adjacent elements. Comparison between two adjacent elements. Yeah, it is a simple, straightforward one, but the drawback with that bubble sort will be if the list is huge. If there are handful of elements to sort, then bubble sort is the best algorithm I can say with very less complexity. But when the number of elements raise, the count of data raises, using bubble sort will increase the time complexity because it's an average time complexity is n square, even though it is a stable one and in place one. Okay, so let's see a new sorting technique, which is selection sort. Selection sort, yes sir. It is repeatedly finds the minimum element. Let's see in ascending order, as I told you in the previous session also, let's confine ourselves to ascending order. Right? Yes. Its best case, worst and average case time complexity is order of n square. Memory it uses is one temporary variable memory, that is just for one. Right? Yes, it is an unstable one and an in place. In place means it doesn't need any extra space, a size of n. If there are n elements in the list, it doesn't need n elements of extra space. No, it doesn't need that. It is not a costly one coming to memory usage. It is in place one. Okay, let's see the algorithm for the same. So, starting from the first element, we start searching for the smallest element in that array and place it as the first position. Freeze that position for that one. Okay, in the remaining list, search for the second smallest element. Place it in the second position. Freeze its position. Right? So, we repeatedly do that. Then how we are going to do that, ma'am? There must be some or the other assumption, right? Yes, the assumption will be by default, the element at 0th index. Let's assume that it is the minimum element. Compare it with the remaining elements. I'll show you with an example. Yes, let's consider the list with 5 elements. I'm making it very simple. I'm not taking a large list, say 10 to 15 elements, and don't want to make a task tedious for you guys. With a simple set of elements, I'll try to explain you the logic. Okay, 5 elements are there. I hope you can see that it is an unsorted list. So, I'm taking 3 pointers. Okay. So, I will be fixed to the element at index 0. J will take the position next to I. Wherever I is, the next will be J. What did I tell you? The minimum element will be, our assumption will be, the minimum element will be the element at index 0. Okay. Now, let's compare. So, I hope you understand this statement. What do you mean by this statement? Array of M. What do you mean by array of M? The element 21 and you are comparing with element 54. Element comparison between element 21 and 54. Is this relation okay or not? If it is okay, make. If the condition satisfies, then make the element pointed by jth index as the smallest element as M. But do you think 21 is greater than 54? No. The condition fails. Okay. Here what is that? A of M is 21 and J is 54. And the condition fails. If the condition fails, there is nothing to do. Just increment the J point. Guys, once again I am telling you, listen to me very carefully. We compare the elements. in the first iteration, we compare the elements pointed by M and J. M and J. If the element pointed by M is greater than element pointed by J, then I am going to change the M pointer to J. M is equal to J. I am going to shift. If the condition fails, even if the condition fails or not, I am going to increment the J value. Okay. So here the condition failed. Okay. So I have incremented the J value. Right. So what happens? Compare between M and J. So here M is 21 and J is 54. Comparison between these two. Condition fails, increment the J value. Once I increment the J value, now J is pointing to 36. So as the condition got failed, the M position will be there itself. It is not going to change. Right? So again I am going to repeat the same. Compare the element placed at index value M, the pointer value M and J. That means here array of M will be 21 and array of J is 36. So is the condition failed or not? Failed. It is because 21 is greater than 36. It's wrong. Condition fails. Simply increment the J value, which I did. So once we increment the J value, now J is pointing to 18. Apply the same old condition. Compare with the element pointed by M and pointed by J. That is here the comparison between 21 and 18. Yes, the condition satisfied because 21 is greater than 18. What we have to do if the condition satisfies? Move the pointer M to J. That we have to do. So now the pointer M position got changed to J. What did I tell you? Even if the condition fails or gets satisfied, we have to increment the pointer J. Right? This is the result of the previous step. Now M is at index 3 and J got incremented and pointed to 29. Same old process we have to continue unless J reaches the maximum index value, which is 4 over here. Okay. So same old condition. Array of M, array of J. Comparison between these two. Here the values are M is holding a value 18 and J is holding the value 29. Is 18 greater than 29? No. The condition fails. So simply increment the J value. Incrementing the J value means what? It is going out of limits. It is going out of limits. Which means we got to the end of iteration 1. So what will be the last step, ma'am? The last step will be swap the elements pointed by M and I. Here I pointer comes into the picture. Swap the elements pointed by I and M. Thereby, why we have swapped that? Why? Because we are searching for the smallest element in the list. And the smallest element, who is holding that smallest element? M is holding the smallest element. Where you have to place that element? You have to place it in the first position. Who is holding the first position? Ith variable is holding the first position. So swap the elements pointed by M and I. Right? So once we swap it, this is what you are going to get. So 18, the smallest element in your list, has come to its right position. I hope you are clear with the first iteration. 18, which is the smallest element, has come to the first position, its right position. Let's start iteration 2. What will be the input for iteration 2? The current list, as this is an in-place sorting algorithm. So I don't have any extra n elements size. So this is the current list. Whatever the list that I have in my hands is the current list. right? Partially sorted current list. That will be the input for my second iteration. So with the incremented I value means now my I is going to point to 54. I'm going to repeat the same process. What I'm going to repeat? Place the M. My assumption will be whatever the element I indicates, variable I points to will be the first assumption of minimum element, or the pointer M pointing element in the current list, in the current sublist, you can say list, right? And J is pointing to the very next element to I. I hope you can see that I and M are pointing to index value 1, whereas J is pointing to index value 2. I hope I am clear till now. Let's see. Same old condition we have to check. Element pointed by M and element pointed by J. A comparison between these two. Here array of M is 54 and array of J is 36. 54 is greater than 36. Yeah, condition satisfied. So what I have to do? I have to shift the position of M to J. And what next? The default one, increment the J value. Whether the condition satisfies or fails, increment the value of J. So now M is going to point to 2 and J is going to point to 3. Right? M is pointing to index value 2 and J is pointing to index value 3. Again, compare the elements pointed by M and J. Here, M is pointing to the value 36 and J is pointing to the value 21. Is 36 greater than 21? Again, condition satisfied. Right? So, change the pointer of M. Now, M is pointing to the element pointed by J. Increment the value of J means what? Now, in the next list, we can see that M is pointing to index value 3 and J is pointing to index value 4. Right? Again, comparison between the element pointed by M and the element pointed by J. Here, element pointed by M is 21 and array of J is 29. Is 21 greater than 29? Condition fails. So we need not change the pointer M. Simply increment J value. But once we increment the J value, it goes out of limits. Once the value of J goes out of limits, what does it say? It tells that the iteration has come to an end. Iteration has come to an end. That is, second iteration has come to an end. Swap the elements pointed by I and M. Pointed by I, M, N. So I have swapped the elements 21 and 54. Then what you can see, the second smallest element in the list, 21, has come to the second position. This is the partial result which I get after iteration 2 in the sorting technique. Okay? So what next? Unless all the elements are sorted, I have to repeat this process. Let's do the same. Iteration 3. In iteration 3, the current list, whatever we have in our hands, will be the input. Right? As this is iteration 3, the result of iteration 1 and 2, that is the two consecutive smallest elements in the list, are in their right position, which are 18 and 21. Their positions are freezed. So from where I have to start my process of comparison? From index value 2. Yes. From index value 2. So I is going to point the index value 2. J is going to point the next element of I, which is 3. Index value 3. J is going to point that element. And our assumption starts with saying that the element pointed by I is the minimum element. As I said, it is an assumption, right? Yes. Start your process. Compare the element pointed by M and J. Here the value at M is 36 and J is 54. Compare with these two. Is 36 greater than 54? No. Condition fails. Simply increment the j value. I incremented it. So now j is pointing to 29. Now j is pointing to 29. Again, comparison between the element pointed by m and j. Here, element at m is 36 and at j is 29. So 36 is greater than 29, condition satisfied. So move the pointer m to j position and increment the j value. We have to do it right both at a time. So my m is pointing to index value 4 now, and once you increment the j value, you are going out of limits, right? What do you mean by out of limits? End of iteration. Once the end of iteration is occurred, swap the elements pointed by m and I. So I am to swap between 29 and 36, which I have done. And by the end of third iteration, the third smallest element, which is 29, has come to its third position or the right position. Okay? This is the end of third iteration. Right? This will, the list which we got, the partial result which we got, will be the input for fourth iteration. As this is fourth iteration, means we have successfully completed 3 iterations. Means 3 smallest elements, consecutive smaller elements in the list are in the right position. I have to start the process from the fourth element. So my I is going to point to index value 3. That is the fourth element. That is, in position wise, it is the fourth element. Index wise, it is the third element. Right? So fourth position element is placed at index value 3. Right? So j will be the next one. So j is pointing to index value 4, and our assumption will be the element pointed by I will be the minimum element in that sublist. Yes. Do the same comparison between the element pointed by m and j. So is here m, you can see that it is pointing to 54 and j is pointing to 36. Is 54 greater than 36? Yes, condition satisfied. Move the pointer. M is going to point 36 now, right? And increment the j value. If you increment the j value, what will happen? Out of limits. Am I right? What do you mean by out of limits? End of iteration. End of iteration. Swap. Swap the elements pointed by I and M. That means I have to swap 36 and 54. And I can see that 36, the fourth element, has come to its right position. So by the end of each iteration, what we were doing? We were incrementing the I value, right? If I increment the I value, it goes out of boundary, because if I increment the I value, it is going to point 54. Am I right? So where j will be placed, think once. It goes out of boundary in the first phase itself, right? So if there are n elements and j will run till n minus 1, then I will run from by n minus 2. Please keep this in mind. If there are n elements, j will run for n minus 1 and I will run till n minus 2. Okay, so here you can see that yes, the total number of elements are 5. 5 minus 2 is 3. So I is at 3, out of limits. Once you increment it, it goes out of limits, right? So this means the end of the logic. So the final sorted list will be the one which we have in our hands, which is 18, 21, 29, 36 and 54. Okay. This is the final sorted list of this sorting technique. I hope you understood this sorting technique. This is a quite simple sorting technique in which we are going to compare the element with an assumption saying that the element pointed by ith variable is the smallest element, and start comparing with all the remaining elements. Okay, so this is a very simple sorting technique. I hope you understood. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.